attending my presentation titled Water Well Rehabilitation Chemicals and Best Practices, a deeper dive into iron bacteria biofouling and mineral scaling. During this presentation, I'll be showing information that's available to everyone from alternate sources. For more information on the ideas and the thoughts in this presentation, feel free to look up many of the references listed, as well as the white paper, Field Comparison of Biofouling Control Measures for In Situ Bioremediation of Groundwater by Evan Cox of Geosyntec Consultants. This gives us a plethora of helpful information about biofouling and its controls. We're going to talk a little bit about what biofouling is, why is biofouling bad, how do you know that you have biofouling as well as scaling, and what do you do to get rid of it? There's a lot of different things that you can do to get rid of these things, biofouling and mineral scaling, and I'd like to go in depth in talking about what those are. What are the differences between different treatment options? And how do you know that you've actually solved your biofouling or your scaling problem? How often do you also need to retreat it? Which is a common question that we get a lot of the times from homeowners and customers. When we talk about biofouling, it's important to categorize what we're actually talking about. Biofouling is described as a microbial growth occurring over a surface in which the individual cells are bound within a common extracellular matrix of polymeric molecules. There are different types of biofouling, and two of the main ones we deal with are iron reducing and sulfate reducing. A dominant group of bacteria are the iron reducing bacteria. Here, the bacteria are unique in that they are able to take up iron and manganese in excessive quantities. The excess is deposited either around the cell, within the slime, or the special structures protecting or extending from the cells. These are deposited as various oxides and/or hydroxides. The slime will generate an orange, red, or brown slime as the bioaccumulated concentration increases. These iron and manganese-rich deposits appear to perform a number of roles, from being protective against predation and physical disruption to even a nutrient reserve. These slimes form sites of intensive oxygen consumption, which may frequently allow anaerobic bacteria to survive and grow within those parts of the slime where oxygen fails to penetrate. In consequence, these slimes may shift to a black phase where there's an oxygen depletion in the environment. Sulfate-reducing bacteria is a common organism often identified in fouled or stagnant well systems. SRBs, as they're known, obtain energy by oxidizing organic compounds and reducing sulfate to hydrogen sulfide. As the hydrogen sulfide is released, the environment often turns acidic, and corrosion can develop as the H2S is mobilized in the well column. Their presence is readily identifiable by their distinctive rotten egg, which is hydrogen sulfide gas that's produced by the bacteria. Within the confines of biofouling, there are different types of slime. Close inspection of the slime reveals that gray and white slime will often consist of a white or a clear slime, within which there are intense black granules. Such black deposits are most commonly metallic sulfides, often iron and manganese, generated by interactions between the various metallic salts and hydrogen sulfide. This hydrogen sulfide may be generated by bacteria growing in the absence of oxygen and reducing sulfur, sulfate, or via protein degraders. These types of slime may be very rich in heterotrophic, which is organic nutrient-using bacteria, and can harbor a wide range of bacteria, including coliforms, where environmental conditions permit. Sulfur-oxidizing bacteria might also form these types of slimes, particularly in a hydrogen sulfide-producing groundwater. This black bacterial flora is dominated by SRBs. Corrosivity is most commonly associated with the black slime due to initiation of electrolytic corrosion by the hydrogen sulfide generated by the microorganisms. Black slime could also include iron-related bacteria with manganese in its biofilm. Because the iron bacteria is sticky in nature, it often incorporates other things. This can look like black slime when it's really manganese that's stuck inside, changing the color from red and orange to dark gray and black. Manganese is a mineral, so it's important when cleaning to understand that you're treating biofouling and mineral scaling when treating black slime. There are different ways to tell if there's biofouling downhole. Using a camera is an easy way to tell if there's iron bacteria biofouling because it has such a strong visual presence. A camera can help you determine where the fouling takes place downhole and how bad the fouling really is. We deal with customers looking for answers to what is downhole, and the one thing you need to make sure of is that you have proper lighting downhole. Depending on how far out you can see with your camera, you'll need to make sure that you have adequate lighting so that the biofouling is visible. The second thing you'll need to make sure of is that you're looking at a color camera. Biofouling is often determined by its color, so if you're looking with a black and white camera, you won't be able to see what you're actually looking at. These images give you a sense of what you're looking at when comparing black and white versus a color camera. It's clear to see that using a color camera can help you determine if it's iron bacteria or if it's even something else. The third thing you'll want to make sure you have is a side view on your camera. Unless you're looking in a very small hole, likely 5 inches or less, a side view will help you see where the biofouling is located and how bad the fouling really is. Using a camera for before and after treatments will help give you a good idea of how well the cleaning really went. BART kits are biological activity reaction tests that determine if iron bacteria is present. There are different BART kits available for other bacterial types as well. Usually, iron bacteria tests involve more invasive water testing, but the BART kits are easy to use and they're inexpensive. The process for using BART kits is to put some of the fouled water into the tube and see how quickly there's a reaction. The reagent inside of the tube reacts with the iron bacteria to turn a dark color within 8 days if the iron bacteria is present. The sooner the color in the tube changes, the higher quantities of iron bacteria there are present. The longer it takes to turn color, the less iron bacteria is present. Another way to test if there's iron bacteria downhole is to test the fouled equipment with chemicals that treat iron bacteria. Later, we'll determine what chemicals actually do treat iron bacteria specifically, but for now, we like to go to a thing called a bucket test. Putting some water with a safe chemical inside of a 5-gallon bucket with the fouled equipment will give you some sort of a reaction if the chemical treats the fouled equipment. The fouled equipment will look cleaner or will be easier to clean after treated with the proper chemical. A water test can be done to test for iron, but there are more invasive tests for iron bacteria. Normal water tests will tell you that there is iron, but having high iron does not necessarily mean that there's high iron bacteria. It's definitely likely, but it's not for sure. It's always safer to get a specific test for iron bacteria than to assume there are high iron bacteria amounts downhole. We find that it's important to talk about how bacterial biofouling actually works and how it becomes one surface. When oxygen in the air mixes with dissolved iron particles in the water, the iron changes to white, then yellow, and finally to red-brown solid particles that can settle out of the water. At a critical point, the bacteria sense that there are significant numbers of them, and it would be more advantageous to act as a group as opposed to acting individually. At this point, the bacteria turn off the planktonic or the unattached portion of their genetic material and turn on the sessile or attached portion of their genetic code. Because iron bacteria is found naturally in groundwater, you'll find it further out in the casing and screens than you might actually anticipate. If you have iron bacteria in the well, it's likely that it will be found in the fractures outside of the screen because it also encounters oxygen there. The biofouling form communities that do not get washed away with the ingress water flow. Iron tends to concentrate closer to the screen, but manganese fouling can accumulate much further out. Biofouling can be very disruptive. One of the ways is that it decreases the well yield from clogged pumps. The biofouling attaches to any surface touching water within the water column, and that also includes the pump. This leads to the pump working harder and ultimately failing because there's no output possible when the pump is completely clogged up. The quality of the water is one of the first ways that people recognize that there are problems within their well. The water will look orange or red or brown and will taste of metal. The water will also have a smell of rotten egg, as sulfur is often trapped inside of the biofilm. Corrosion does more than damage the pipes. It can precipitate into the water and cause health problems. The iron bacteria itself is not a health hazard, but what comes from the iron bacteria biofilm can be hazardous. As the biofilm matures, the stratification of the slime occurs. The demands of the biofilm for oxygen exceed the amounts being carried into the water flowing by. Consequently, the deeper layers become oxygen starved and turn anaerobic. This causes the microorganisms to flourish under environments free of oxygen, ready to dominate. Two primary layers are created. Aerobic organisms form a layer closest to the water, which is their source of oxygen, and the anaerobic move to the deepest layer, where the water doesn't penetrate. In between, there is a transitional layer that's sometimes oxidative, but sometimes reductive. These layers make it very difficult for chemicals to penetrate. That's why there's a two-pronged approach to treating biofilms, using chemicals and physical agitation. Another response commonly seen in a maturing biofilm is the stratification of the biofilm, in which the primary layering differentiates an exposed aerobic, oxygen present, stratum overlayering and protecting lower anaerobic, which is no oxygen present layers. These lower surface interfacing layers are often biologically generating hydrogen sulfide or organic acids, which can then initiate the process of corrosion. Flow restrictions become enhanced wherever the water touches. This means that all piping and equipment can be fouled and clogged. Severe restrictions are classified as 75% restricted flow. Once the flow is restricted this much, it can be very difficult to clear out or repair. A lot of people assume that if their pump isn't working, it's all the same problem, especially if it's biofouling. If careful considerations are taken, these things won't be mistaken for bacterial biofouling. Often homeowners and those in the industry refer to iron bacteria as soluble iron, but there's a difference between iron bacteria and iron that you naturally find in the water. Some iron in water is good, but high levels can be dangerous. Because of its coloring, iron bacteria is sometimes mistaken for rust or silt. Although rust is iron oxide, it's not the exact same thing as bacterial biofouling. When silt enters equipment or the screen, there's cause for concern because it's very difficult to remove. Because it's not a bacterial formation, it will not be able to be removed by standard biofouling removal procedures. Lastly, iron bacteria itself is not a harmful bacteria. It's found naturally in the groundwater and it's safe to consume. When biofilms are produced, however, it can harbor harmful bacteria, and that's why ridding a water system of any biofouling should be a top priority. We work with customers all over the world who experience biofouling issues, and there are hardly two people that call it the same thing. It's important to remember that just because a customer calls it iron algae doesn't mean that they're actually talking about algae. They may mean iron bacteria, but don't have the right words to explain it. Often we'll ask customers to describe the biofouling or to send us a picture so that we're all on the same page. Homeowners get most of their information online, and if you look up iron bacteria online, the World Wide Web will also call it many different things. Don't get hung up just on what it's called. Just make sure to clarify with what your customer is actually talking about. There are two main types of iron bacteria as well, planktonic and sessile. Planktonic bacteria is free-floating in the well, where they will look like small particles unattached. On the other end, sessile bacteria are attached to a surface, and that's what starts to make up your biofouling. Biofouling can really be found anywhere that there's a water source and soluble iron. Any water well can have this issue, and it includes all of the equipment associated with it, pumps, pipes, and casings, and as we talked about further, out into the screens. This bacteria does not keep to just one place. Piping to a house and the water equipment associated with it are also at risk for fouling. This is one of the main reasons it's important to keep up on the maintenance of the well itself, to prevent the biofouling from happening further on into the house. Most recently, we've seen an uptick in the basement waterproofing industry looking for answers to iron bacteria problems. Because basements have water that flows into the drainage and sump pumps, the piping and the sump become clogged with iron bacteria. It's widely misunderstood in the basement waterproofing industry, and often people spend thousands upon thousands of dollars to remove the piping and the sump just to relieve the clogging. I consistently talk to homeowners who change their sump pump every single year because they're not informed as to how to even treat iron bacteria. Water treatment centers are no exception. The fouling is caught in membranes and filters alike. These difficult to reach and immensely complex treatment centers spend a lot of money repairing and replacing equipment that's fouled. This is a map from the USGS in 2010. This map gives us a broad overview of where iron bacteria is known to be present. In dark red, it shows us the severe locations. The light red shows us the moderately contaminated places, and the white represents what we call the great false negative. This white space is expansive, but it leaves out a lot of iron bacteria information. If you've ever experienced a customer or a homeowner who has iron bacteria in their water system, they might tell you of how their neighbors either all have the same issue or they've never seen it before, and neither has their community. This mostly happens in more rural places where residential wells are located. The white space is the great false negative because biofouling travels throughout the groundwater and can be placed in a new well by contaminated equipment. There's no real way of knowing where iron bacteria is not, because testing isn't accurately done by homeowners or contractors alike. There are different ways of treating iron bacteria, and because it's been studied a lot more in the last few decades, there's more opportunity for advancement in treating options. There are three main ways that we're going to look at treating iron bacteria. The first is via chemicals. This is a very common way that requires research into the proper chemical and its advantages or disadvantages. Chemicals can be highly toxic, so it's important to ask a lot of questions when choosing one. Treating a well with physical equipment and stressing the bacteria are also options that we'll get into. First, let's take a look at treating biofouling with a chemical. Before any treatment's done with a chemical downhole, there are certain questions that should be asked to ensure that the chemical is safe for use and will be the best product for your particular job. These questions were derived from Michael Schneiders, who's a mainstay educator in the groundwater industry. He asks the right questions that we should all be asking when planning treatment. First, let's identify the problem. Have they used a camera to see the problem downhole? How do they know what the problem is? It's important to understand what the issue is before choosing a product to treat it. There's hardly a one-size-fits-all when it comes to chemicals. Doing your research to confirm that the right chemical is being used. Does this chemical specifically treat the problem? The structure of the well matters. Is it based in limestone or rock? This might affect the chemical's efficacy and the dosing requirements needed. Confirming the instructions for use. Does the pump need to be removed and special surging done? Does it need to be diluted, pre or post-treatment? All of these things will count into how expensive and how long the treatment will actually take. Researching the environmental and equipment impacts. The stronger the acid, the more precautions that need to be taken. Will the chemical affect a pond, a lake, or a river nearby? Is there an inhibitor included with the chemical to safeguard your equipment? Choosing a product that's safe is becoming more and more of a priority, and for good reason. Just imagine that whatever you put down into the well is going to have trace amounts of leftovers, and the hazardous materials should be minimized as much as possible. All chemicals are not the same. Chemicals differ not only by what is in them, but how they're used. When planning a treatment course, it's important to look into what each chemical needs in order to succeed and hazards to avoid. The type of equipment used will differ with chemicals because you need to brush, you might not need to, it depends on how bad the problem really is. For most applications, it's beneficial to combine chemical and physical equipment, but it does depend on the issue. Most chemicals have severe and maintenance dosages, which give you a full or a partial amount of product to use for your application. These can be worked out with the chemical company. Oftentimes, it's useful to have water tests done so that amounts of scaling or biofouling are known and a dosage amount can be administered. If your customer is not able to have a well out for a full 24 to 48 hours, then you might consider doing 2 treatments instead of 1. The upside to doing this is that within your initial treatment, though half of the sitting time is used, you may have a clean enough well to pull off the second dosage. Using the camera or doing a post-treatment water test will always determine if this is the right option for this project. Different chemicals require different contact times. Always check with your chemical provider for more information on what's recommended. As we discussed earlier, using mechanical methods in addition to chemical methods will always get you a better clean. Being able to push the chemical out into the formation might be expensive and time-consuming now, but it will give you a better clean for longer. The well volume is important because this aids in the dosing requirements. How often do your customers who don't know how deep their well is? If this information is unknown, it's important to retrieve it because you don't want to underdose or overdose the well. Overdosing can have hazardous implications, and underdosing will leave the customer and you upset and frustrated, since a second or alternate treatment will need to be done. Lastly, the pH requirements of the chosen chemical is important because the chemical is really only as good as the pH is stable. Checking the pH before, during, and after treatment will give you a good baseline. There may be chemical products that you're used to for using a plethora of issues, but it's good to know what the actual active acid is inside of the product being used, because that can be the difference between a successful clean and a so-so clean. This chart gives us a look at some of the common acids and what they are good for. Green acids on the right are known as organic acids, which gives them the ability to biodegrade naturally. The highlighted portion in blue shows the efficacy against biofilm and iron oxides. And looking at the treatment of biofilms, all three red acids, sulfamic, hydrochloric, and phosphoric, are listed as poor. This makes sense because they're not organic and they're not able to penetrate the biofilms, which we've learned is not as simple as just throwing a low pH acid at it. Hydroxyacetic and oxalic acids are listed as moderately good acids at cleaning biofilms. There are differences between the two acids, though they're both good at treating biofilms. You'll notice the differences in the rows listed above. Hydroxyacetic is a fairly weak acid, but cleans biofilms and scale well when combined with a chemical like sulfamic acid. Oxalic acid is a moderately strong organic acid, but just like hydroxyacetic, it'll need a scale inhibitor when treating both scale and biofilms. These organic acids are not meant to treat both biofilms and scale at the same time. Often, hydrochloric acid is used to treat biofilms, but there's research to prove that this shouldn't be done, especially without a mixture of a different chemical. Hydrochloric acid can be very strong and hazardous, so the utmost precaution should be taken when using it. Here's what some other people had to say about it. It should be noted that muriatic acid as a biocide is relatively ineffective because it is ineffective against biofilm polymers. Regrowth occurs rapidly after treatments with this acid alone. Hydrochloric acid solution will remove or loosen incrustation in the screens or the column pipe, although it won't remove much biofouling. Stuart Smith of Groundwater Sciences says, muriatic acid is supposed to remove the iron oxides. However, it tends to flash dissolve the minerals it touches first, without much penetration, if not amended by other products. This leads to the condition where good performance recovery fades quickly. Oxalic acid is known to remove biofouling well, and it's a strong acid when not mixed with inhibitors. It's biodegradable, which makes it a safer choice for treating biofouling downhole, but precautions still need to be taken. Using oxalic acid by itself in a hole with mineral buildup can produce calcium oxalate, which can be difficult to remove. The recommendation is to pair this chemical with a mineral scale removal product to treat both the iron bacteria and the mineral scaling. For biofouling treatments, it's important to know what formation the well is sat in. If a biofouled well is sat in a limestone formation, you'll want to make sure to use a scale removal product as well as a biofouling reducer to treat both issues and not end up with a sour byproduct. Iron-related bacteria and sulfate-reducing bacteria are coated in thick layers and are protected by their slime. Shock chlorination may kill some surface-level cells, but the rest are left untouched. Chlorine removes extracellular polymers and not biofilm cells, leaving biofilm cells more exposed to the nutrients, which is the oxygen in the water, once the cleaning is finished. Their surviving cells rapidly create more slime as a protective response to irritation by chlorine. Iron dissolved in the water may also absorb the disinfectant before it reaches the bacterial fouling, basically rendering it useless. 1,000 parts per million of chlorine can be recommended, but these levels promote chloroforms. This much chlorine will likely agitate the biofilm as before, making it reproduce quicker. Strong chlorine solutions used for shock chlorination may damage biofilms but will not kill all the organisms in them, since the chlorine cannot fully penetrate inside or destroy all the slime filament-like structures. One of the main reasons people use chlorine on biofilms is because it's so cheap. This is true. You can get chlorine at a fraction of the cost of specialty chemicals, but the issue is, what will it cost in the long run? Using chlorine to treat biofouling might give you an initial clean, but over time it'll stop working and it will cause more problems than it helps. This leads to an expensive fix later on. Here are some quotes on what others have to say about using chlorine on bacterial formations. There are two major concerns: that chlorine has little ability to penetrate biofilm structure, and that the oxidation potential of chlorine is not target specific, and much of the disinfecting properties may be neutralized by other oxidations of dead organic materials. This is what it looks like when the iron in the water uses the chlorine's disinfecting properties. It doesn't let it reach the biofilm. OxyChem states that chlorine is known to be relatively ineffective at controlling slime. It doesn't penetrate the slime layer, but it only works on the surface, burning off layer after layer. Chlorine's ineffective if there's sufficient bacterial nutrient so that the rate of bacterial production is higher than the rate of biofilm removal by chlorine. H2O2 and calcium hypochlorite treatments were effective, but short-lived in their effectiveness for controlling biofouling. There are many different ways of treating a well mechanically, and it can be useful when treating it for biofouling, as typically one treatment option alone doesn't give a sufficient clean. Brushing and surging can give good cleans when used with chemicals. Alone, they're not able to penetrate the filter pack, but when used with chemicals, they'll push the chemical further out into the formation and clean the filter pack, and possibly further. This allows for a longer clean. Jetting can be a very effective means of treating biofouling, as it uses high-pressure water or fluids to clear out the casings and screens. There's special equipment involved, and it's not always the easiest setup. AquaGuard is a fairly new project when comparing with previous options, but it's effective on biofouling downhole. There are more vendors that utilize this technology, and it's becoming more widespread than before. One of the benefits of this method is that there's little to no toxic byproducts, which is safer for the environment. Though there are a lot of different types of physical removal methods, mechanical removal is not the total solution. Though it will help decrease the amount of bifouling in the short term, it doesn't reach into the filter pack long enough to give long-term relief. If biofouling is left to mature, it may be too hard for any physical applications to knock it down, and it'll need a chemical reaction to make it soluble. The picture on the right shows where biofouling, in the dark gray color, can occur. Using solely mechanical efforts won't treat the further outside of the well screen, and using solely chemicals without proper agitation will leave those same places mostly untouched. Combined efforts of mechanical and chemical treatments can get you the best clean. Heat addition can also improve the effectiveness of chemical well rehabilitation treatments. Because heat allows chemicals and products to become more soluble, it allows them to work faster, up to a certain point. Pouring scalding hot water downhole is not going to make a 24-hour treatment last only 4 hours. Chemicals need time to work, and heat doesn't make it significantly quicker. Aquifer materials subject to regular heating can store heat, which can cause grout to dry out and crack. Excessive heat isn't favorable for most plastic components used in wells, but temperatures applied at less than 140 degrees in the well are still within the tolerance of any PVC casings. The other part of this is that if misapplied, heating can encourage growth at the edge of the thermal impact zone and possibly increase biofouling within the aquifer. A main issue with stressing the bacteria is that the bacteria has short life cycles, probably about 20 minutes, which allows them to have a high level of adaptability to environmental changes. William Gerakoulis, who's seen as a biofilm expert, did research that shows that biofilm recovers from stressing and is able to adapt quicker to it in the future. There are different ways of treating mineral scaling, and because it's easier to treat, those methods are more widespread. Similar to the iron bacteria map from the USGS in 2010, they also put out a calcium hardness map. It's clear that everyone deals with some form of hardness. Others just have a much worse problem. When looking to test for calcium scaling, hard water is a good indicator of scaling. A simple water test can tell you if you have hard water, and this can tell you whether you have scale buildup downhole as well. Luckily, there are more options to treat scale than there are for iron bacterias. Calcium in hard water is ubiquitous across the nation. As we saw on the map, certain places are more prone to having hard water than others, but overall, everyone deals with it on some level. As it does in biofouling, having too much scale can be a bad thing. Mineral buildup includes calcium and manganese, among others. This also depends on where the well is placed. If it's placed in limestone, it's likely to have a higher mineral buildup rate because of the solubility of the minerals exceeded. We see this in a state like Iowa, who has high amounts of iron bacteria, but also high amounts of calcium. In order to treat both of these issues, they need to use mineral scale and iron bacteria products, as there's hardly a treatment for both in just one product. What causes scale to begin with? A scale is the result of an oversaturation of calcium carbonate, which is naturally in water. The water can't hold more calcium carbonate in solution after it's completely saturated, so it deposits calcium carbonate. Imperfections on walls down hole leave further room for the mineral to take hold. This is seen regularly in casings as the slots act as ledges for minerals to land. Orinda Technologies online says that calcium carbonate scale occurs when hard water meets high alkalinity and warm temperature, which allows for the dissolved minerals to leave their dissolved state and resolidify. In other words, when the pH and the temperature are high enough, hard water's minerals can harden and attach to surfaces. Once minerals have begun to attach and resolidify, that's when the buildup begins. Slight scaling can be considered beneficial in that the inside surfaces of metals and pipes can become coated with the harmless minerals that act as a barrier to corrosion. Increased levels of scaling, however, can be harmful. Mineral buildup causes problems mainly within its restrictions. As biofouling contaminates the entire water system, so does mineral scaling. Mineral scaling builds up on itself as saturation decreases and restrictions become more enhanced. The more time that the piping or equipment is left untreated, the larger the problems become. Severely restricted pipes and tubes are difficult to clean and sometimes very difficult to repair. When looking to treat calcium buildup, one of the biggest factors is the pH level and how quickly it can dissolve calcium carbonate. This chart shows us at the bottom the amount of acid at 100% strength required to dissolve a pound of calcium carbonate. Sulfamic acid shows us 2 pounds, hydrochloric at 0.73 pounds, and phosphoric at 0.65. This tells us that there's less product required from phosphoric and hydrochloric as opposed to sulfamic. These numbers play into dosage amounts, whether you will need more of a product or less. Your chemical company can help you determine the amount of product needed. It should be noted that the organic acids are not very good at dissolving calcium carbonate. Though oxalic acid has a low pH, when dissolved in high calcium carbonate supplies, it can form calcium oxalate. The best way to avoid a scenario like this is to test your well properly and to use a scale inhibitor as well as an iron bacteria reducer. One of the main reasons why hydrochloric acid is so successful at treating carbonate scale is because of its low pH. When treating well with a product that requires a low pH, you'll want to make sure that the pH is checked every few hours to make sure it's not spent. Once the pH starts to return back to normal, that means that your acid is no longer working on the scale. At that point, you should check with your chemical provider to see if putting more acid into the water supply or dumping and retreating is better. This is a good reason to always check the pH at the beginning of the treatment. Having a baseline will help you determine where the pH is heading towards and when the product is spent. There can be a lot of time wasted if your pH is spent downhole after 10 hours and the well ends up being off for 24. This saves you time and your customer time and money from having to do the treatment a second time on a later date. This video shows what mineral scaling looks like when hydrochloric is introduced into a bucket. The resulting bubbles are from the acid interacting with the mineral, which produce carbon dioxide. This is a good reason to try doing a bucket test to tell whether this is a mineral scaling problem or something else. This low cost-effective pre-treatment option will help you save time and money in the long run. Products with sulfamic acid in them are good to use against mineral scaling, but not against biofouling. It's relatively safer to use on calcium carbonate than muriatic acid, but it should still be used with caution. Because hydrochloric acid is so strong, sulfamic acid is sometimes used instead. It's often mixed with other acids in a product to treat multiple things because it's not as highly corrosive as hydrochloric. Although helpful in removing scale, when used, Phosphoric acids can be left behind on minerals or residual iron or manganese hydroxides, and when chlorinating, can be a nutrient boost for regrowth. This poses further issues about working towards a long-term clean. Yes, phosphoric is an inexpensive acid to use in well rehabilitation, but the implications aren't as simple. There are multiple ways to verify that a treatment has been done successfully. In addition to checking that the pH levels have stabilized, the first is to camera the well. Using a downhole color camera with a side view will help the finalization process by checking that the casings, pipes, and planktonic bacteria are cleaned off properly and that there are no large spots untreated. This is a great time to do a verification check on well itself and to make sure that the structure is still intact, as well as giving you a video confirmation that a job has been well done. A picture truly is worth 1,000 words, especially when it's something that they have never seen before. A video or an image of the before and the after treatment downhole will go a long ways in proving that your company is not only a well-established and professional company, but that you double-check your work, as well as have a copy on file of the video for future needs. Images and videos come in handy when they're legal matters. It's really hard to dispute a video. For bacterial issues, using a BART kit is a good way to keep a new baseline. We recommend using a BART kit before your treatment to tell you how bad your iron bacteria problems are, and a BART kit after treatment to make sure that your levels have declined drastically. The second BART kit will give you your new baseline to compare to in the future when using the kits to check iron bacteria levels. Once the results start to let you know that the levels are raising, it's a good time to start the process of retreating the well, as this will be something you'll need to do continually. A standard water sample test can be a simple way of determining that a job is well done. In addition to the previous methods, a water sample will give you a new baseline, something to compare to your pre-treatment water sample. These can be done at any local or nationwide lab and will be good to hold on to in case the house is sold or is needed for insurance purposes. Lastly, if possible, check it with your own eyes. Visual verification of equipment, if you're able to reach or see it, is going to tell you a lot about how the treatment went. This is recommended in addition to one or more of the previous methods, but it's certainly the easiest. Putting together a maintenance plan is necessary for keeping pumps and water wells functioning correctly. The phrase, failing to plan is a plan to fail, rings true here. If a plan isn't implemented to continuously check and clean a well over a period of time, there will be buildup and corrosion that's likely to come. It will be costly and it will be difficult to remove because of the stratification layers that occur when the deposits are left after a long period of time. The best way to get ahead of this is to regularly clean the well. It depends on how big the issue is in each area. Some areas need to be checked and maintained every 8 months, some need it only every 2 years. That's why it's a good idea to get water samples and to have visual verification every once in a while just to stay on top of those issues. Combining the practices that we discussed is where the future of well rehabilitation is going. The days of just picking up chlorine because it's the cheapest and throwing it down a well are long gone, and for good reason. The technologies that are available for providing clean groundwater are closer and easier to understand than ever. First, we want to see what's going on downhole. This is always best coupled with some sort of water sample test to ensure that we know what the issues are at hand. Then, we want to choose and treat the well with the proper chemical. Utilize the aforementioned questions to help choose the best chemical. Afterwards, we want to verify that the treatment has been done properly. You can do this via a camera survey, a water sample test, a BART test, or even visual verification. We recommend doing this within 48 hours of the finished treatment to give you a good baseline for the future. After that, we recommend monitoring regularly and comparing it to the baseline you gathered post-treatment. This will give you and your customer understanding what issues may come and may be able to deal with the fouling or scaling much more easily, rather than just having to do a severe treatment dosage every few years. I've used a number of different sources across the internet, and I wanted to make sure that you know where you can find them. As in life, it's always good to gain information from different locations, and so this will give us a better idea of what to do next. Thank you so much for listening to my presentation. I hope you learned a little bit about biofouling and mineral scaling and what to do when you encounter them. There's a whole world downhole, and these topics really only scratch the surface. If you have any questions, please feel free to reach out to me via my email or my cell. I'd be happy to discuss any chemical or CAMA questions that you may have. Again, my name is Kristina from Laval Ground Surveys. On behalf of all of us here, thank you very much.